In this video, we're going to talk about functions and relations, what exactly they are, what's the difference between the two, how can we tell if something's a function or not, and finding the domain and range of various functions. We're going to start right away with a definition. Our definition is the definition of a relation. A set of ordered pairs, x, y, is called a relation in x and y. And the set of all the x values is called the domain of the relation. And the set of all the y values is called the range of the relation. So x values is domain, and y values is range. So relations can really be about anything. It's just a set of ordered pairs. These ordered pairs usually in mathematics contain numbers, but they can be anything we want. We can have ordered pairs with names in them, names and places, things like that. It really doesn't matter. It's just a way of relating two quantities. So most of the time we're going to be using numbers, and we're relating the number x and the number y together. So let's start with an example. So I'm going to give us a table that we're going to use for this example. It's going to have x values and y values. And let's just get a couple more values in our table. And the first thing we're going to do is write the set of ordered pairs for this relation. So when you see a problem like this, you have to just make sure you don't think too hard. All this is asking us to do is take the information in the table and write it a different way. We're going to write it as a bunch of ordered pairs, x, comma, y. So to make a set of ordered pairs, you need these curly braces. They can be a little difficult to draw, but you'll get the hang of it the more times you try to draw these. So one of my ordered pairs that would go in here is x is 3 and y is -4. I have another ordered pair, -2 and 0. And then 5 with 3 and 1 with 0. So I have a set that contains 4 different ordered pairs, and this is the relation represented by the table. Not too complicated, it's just a matter of making sure you put the x's in the first spot and the y's in the second spot. Now something that's a little bit more tricky sometimes, the domain and the range. So when we just have distinct values like this, we can write the domain and the range as just a set with the exact values for all the x's and y's with commas in between. So I'm going to start with my domain. Remember that your domain is x values. So I'm going to have the set of all of my x values. We can look at the table or at our points, our ordered pairs, to find the x values. Regardless, it's 3, -2, 5, and 1. And now for the range, we need all of our y values. And if I list all my y values, I have -4, 0, and 3. There's no need to write 0 down a second time because 0 is already represented in the set. When you're writing down a set of values, you don't have to repeat values. Just one time for each value is more than enough. Well, not more than enough. It's exactly what you need. Just one time for each value. Now, notice in these domain and range sets here, there's really no particular order that I wrote them in, and that's because when you're writing sets like this, the order doesn't matter. It doesn't matter if I wrote my domain as -2, 1, 3, 5, so it was going from smallest to largest, it would still be the exact same set. So the order doesn't matter, and you should not repeat your elements. All right, so now we know a little bit about relations. Now we have to talk about a special type of relation called a function. We work with functions an awful lot in mathematics, so it's very important to know what they are. So, definition of a function. Given a relation in x and y, we say that y is a function of x if for each value of x in the domain, there is exactly one y value in the range. So this definition sounds actually more complicated than it is. All this is saying is if you have an x value in your relation, it should only match up with one y value if you're trying to have a function. Functions take your x values and pair it up with a y value. And the x value can only be paired with one thing. So if you have a set of ordered pairs like we had before for our relation, and your x values repeat and they go to different y values, that's not a function. But as long as each x value only goes to one y value, you have a function. Let's do an example deciding if a relation is a function or not. So our question is y a function of x? And here's our first relation that we're going to consider. We have 8, 4, 3, -1, and 5, 4. Is this a function or not? Well, the answer to this is yes, it is a function. The reason that I know that is because if I look at my x values, I have 8, I have 3, and I have 5. All of my x values are different. None of them are repeating, so I don't have the same x value being mapped to a different y value. It's okay that I have a 4 here and a 4 over there. That's perfectly fine. There's nothing preventing the same y value being assigned to multiple x values. If you have a function, it's just that each x value is only assigned one y value. Let's do another one. How about the relation -3, 2, 9, 5, 1, 0, and -3, 1? Is this relation a function? Well, the answer to this one is no, and a lot of you are probably saying that because you're going to assume that if I gave an example where it is a function, I'm also going to give an example that's not a function, and that's correct. But we should figure out why this is not a function and not just because I haven't done an example of that yet. This is not a function because when we look at the x values, well, here I have -3, here I have 9, here I have 1, but my fourth ordered pair, I have -3 again. So I have 2 times that I have -3 as my x value, but the y values are different. I have 2 and I have 1. 2 is not equal to 1. This is not a function. It's not a function because I have the same x value, -3, paired up with 2 different y values, and that is not what a function is by the definition of a function. All right, well, that's not too terrible. That's actually a pretty easy way to figure out if something's a function or not, but of course, in math, we always have to go and make things harder. You're not always going to have relations and functions listed as ordered pairs. We have functions that are sometimes listed as an equation. Sometimes we are just given a graph. How do we know if something's a function when they're not given to us as ordered pairs? Well, if it's given to you as a graph, you can tell if this is a function or not by using what's called the vertical line test. So let's learn about that. The vertical line test says that a relation that is graphed is a function if no vertical line intersects the graph in more than one point. So to tell if a relation is a function or not when you're given the graph, just imagine vertical lines being drawn through the graph. See if it hits in more than one point. If there is even one vertical line that touches the graph more than once, it's not a function. In order for it to be a function, every single possible vertical line has to touch the graph at most one time. So let's do some examples where we look at some graphs and use this particular vertical line test. So, is each relation a function? I'm going to have 3 different ones, but we're going to just start with A and B, and I'll do C after I erase my board. So I'm going to draw 2 graphs here, and I'm going to graph our relation, our potential function, in red. So for A, I'm going to have this relation, and for B, I'm going to have this relation. And let's start with A. Is this a function? We're going to use the vertical line test to find out. Remember, the vertical line test just says that if a vertical line is drawn through the graph and it touches the graph more than one time, we don't have a function. So I like to take my pencil and just drag it across the page and see if it ever is going to intersect the graph more than once. And we can see that that happens a lot. So here's just one example of a vertical line that's intersecting the graph of my function in 2 different points. So by the vertical line test, this is not a function. Let's do the same thing with B. If you take your pencil and go from left to right, dragging it across your graph, does it ever touch the graph at more than one point at a time? No. I can draw a few lines just as an example. Here's a vertical line, it touches once. Here's a vertical line that touches once. Vertical line that touches once. No matter where I draw a vertical line, it's only going to touch my graph at one point. So this is a function. Okay, so those two aren't too bad, but part C is the trickiest one of the three examples. So let's go ahead and do the tricky one. Part C, I have a kind of strange looking function. Well, I might have given it away, but function or relation, well, we're going to find out after it's graphed. Here is what this relation looks like. I'm going to graph it in red again. This one's a little stranger looking, but to figure out if it's a function or not, we're still going to do the exact same thing that we did on the other ones. We're going to take our pencil and go left to right and see if a vertical line ever touches more than once. And really, there's only one place that you should be a little bit concerned about. If I draw a vertical line over here, it's fine. It touches just one time. Same with over here. The only place that you might be a little bit concerned about is if I draw a vertical line right here. Does this touch my graph more than one time? Kind of a trick question, but it does not touch my graph more than once because this open circle here means there's not actually a point there, but the closed circle means there is a point. So even though it looks like it might touch more than once, since I have an open circle there, there's no part of my graph actually being touched up top. It's only being touched right here. So is this a function? Yes, it is. So that's how we use our vertical line test. I'm sure most of you would really love to have an exam where the entire exam is vertical line test problems. They're really not too bad. All right. Let's keep finding out if various relations are functions or not, but this time, not going to be a set of ordered pairs, and it's not going to be a graph. So we have to try to use what we know about relations and functions to figure out if these things are just relations or if they're also functions. Part A. Here's my relation. I have x values 2, 3, and 8, and I have a y value of 4, and my relation is indicated by these arrows. 2 is going to 4, 3 is going to 4, and 8 is going to 4. Is that a function? Yes, it is. It's okay that I have x values all going to the same y value. Remember, for it to be a function, we just have to make sure each x only goes to one y. It does not say that each x has to go to a unique y. It's just each x has to go to one y, and they could all go to the same y if we want. So this is a function. How about one that's written as an equation? Here's a relation. Absolute value of y plus 1 equals x. Is this a way of writing y as a function of x? Well, to figure that out, let's first solve for y to try to make it look a little more like we're used to. If we have absolute value of y plus 1 equals x, that means by the definition of absolute value that y plus 1 equals x or y plus 1 equals negative x. And if I solve this for y by subtracting 1 from both sides of the equation, I get y equals x minus 1 or y equals negative x minus 1. So if I were to take x values and plug it in, I'm going to get two different y values potentially. So let me do just an example. For example, if I use x is 1, then we have that y is equal to 1 minus 1, which is 0, or y is equal to negative 1 minus 1, which is negative 2. So I have the same x value going to two different y values. Is y a function of x? No, it is not. because I have the same x value going to more than one y value. Let's do one more. You could have also done that second one by graphing, maybe make a table of points, graph it, and then use your vertical line test. That's perfectly fine as well. Part C, I have x squared plus y squared equals 25. Is that a function? It's a relation for sure, but is it a function? The answer to this is no. If I were to graph this, it's a circle that has radius 5, centered right at 0, 0. So then you could look at the vertical line test and see that this is not a function. So this equation is a circle. So it's not a function. All right. So we've talked a lot about functions and relations. We have to learn something that sometimes confuses people, something called function notation. It's a way of writing our equations in a special notation to indicate that this is indeed a function. So function notation. I'm just going to use an example to help us learn it. Y equals x minus 2 is a function of x. And this can be written as this notation here. And this is read out loud as f of x equals x minus 2. So this right here is saying f of x. It is not f times x, and that's the most common mistake that we see among students. This is just saying f is the name of my function, x is my input, and f of x is my output. So let's get some practice with this function notation. We are going to evaluate the function h of x equals 4x minus 3, and we're going to plug in a lot of different x values to see what we get. So I know I was just talking about f of x, and now I'm calling it h. That's just because we like to use different names for different functions sometimes. F is very common, so is g and h, but really you can use any variable that you want, well, any letter that you want to stand for the name of the function. It's just lowercase American alphabet letters are very, very common, especially F, G, and H. Those, I think, are the most common function names. So we have h of x is 4x minus 3, and the first thing that we want to do is find what is h of negative 3. So remember, this is not saying h times negative 3. This is saying take what you have for h of x, and every single place where you see an x in our function definition, we're going to replace it with negative 3. So we're going to plug that in for our x. So everywhere I had an x, I now put a negative 3, and then we just have to simplify. This is negative 12 minus 3, which is negative 15. And what this means is if I were to graph this function, I would have a point on my graph at negative 3, comma, negative 15. So there's a point on my graph that is x is negative 3, y is negative 15. Let's just do another couple just to make sure we remember that this is not multiplication. All right, let's do h of 0. So remember, this just means everywhere you have an x, you're now going to replace it with a 0. So I get 4 times 0 minus 3, which of course is 0 minus 3, or negative 3. This means that we have a point 0, negative 3 on the graph of this function. One last one for practice, h of 1. And again, this just means replace every single x with a 1. So I get 4 times 1, which is 4, minus 3, and I get an answer of 1. My y value, or my output, is 1. All right, so those aren't too bad, but what if we're not going to plug numbers into a function? What if I plug in something different than a number? So we're going to use a different function. This one's named f. It is negative x squared plus 4x. And we're going to evaluate this function for 2 different values. Our first one is f of a. Now, this really is only going to confuse you if you're thinking too hard. Remember what it means with this notation. When we had numbers in there, if this was f of 2, what you would do is replace every single x with a 2. We're going to do the same thing here, it's just we're replacing every single x with an a. So everywhere I have an x, I now put a. And I get f of a is negative a squared plus 4a. And that's all we can do with it. One thing that students tend to struggle with a little bit on some of these problems in pre-calc is you don't always get answers that are just a number anymore. Sometimes you get some complicated looking things, and that's okay. Remember, we're getting ready for calculus in this course, so things are going to get more complicated. Let's do one more with this function. And this particular next example here is very, very important for calculus. We're going to find f of x plus h. You're going to see a lot of f of x plus h's if you take calculus 1. You're going to learn it pretty much right at the beginning of the semester. This comes up all the time. So it's good that we get used to it now. F of x plus h, just using what our function notation means, says replace every single x in the problem with an x plus h. So all that I did there is I know I have f of something equals negative something squared plus 4 times something. And this time my something just happens to be x plus h. So you put it in parentheses and have negative parentheses x plus h squared plus 4 times x plus h in parentheses. And we can simplify this by distributing. So the first thing I'm going to do to try to simplify this a little bit is, just to be safe, I'm going to rewrite my x plus h squared as x plus h times x plus h. Just because I know it's all too common for students to forget when they're squaring something like this, they forget to distribute everything. And then they miss the middle term that you get when you distribute. So we are going to distribute everything in this problem. So I get an x times an x times h times x, and h times h. And I'm also going to distribute this 4 onto my x plus h. So when I do all of that multiplication, I have a negative, x times x is x squared, x times h is x times h times x is also x times h, our order doesn't matter, so I have 2x h times h is h squared, I have a 4x, and I have a 4h. And the only thing that's left to do is distribute my negative sign. So I get negative x squared minus 2xh minus h squared plus 4x plus 4h. At this point, you would try to combine like terms if you had any. This particular problem, though, we don't have any like terms. So you just put a box around it and you're finished. All right, so that gave us a little bit of practice trying to figure out what this function notation means and how to deal with it. Now we need to learn a little bit more about our functions, because eventually in this class we're going to do a lot of graphing with functions, so we need to learn some things like x and y intercepts. So x and y intercepts. The x-intercepts are the real solutions to the equation f of x equals 0. The y-intercept is given by f of 0. So what are these intercepts? It's where the graph of our function touches our x or y axis. The x-intercepts, which you can have more than one of those, is where the graph of your function touches the x-axis, that horizontal axis. And the y-intercept, you can only have one of those, and you might have none. The y-intercept is where it touches the y-axis. So let's do an example finding these intercepts. Find the x and y intercepts of f of x equals absolute value of x minus 5. And now it doesn't matter which order we do this in. We can find the x-intercepts first or the y-intercepts first. I personally usually find my y-intercept first because I think it's a little bit easier. So y-intercepts, remember that is where you plug in a 0 for your x, f of 0. So that's absolute value of 0 minus 5, which of course is negative 5. This means that my y-intercept is the point, x is 0, y is negative 5. Now to find my x-intercepts, we have to do a little bit more work. Your x-intercepts, remember, are solutions to the equation f of x, which is absolute value of x minus 5, equals 0. So this time our y value is 0. To solve this, I'm going to add 5 to both sides. Get absolute value of x is 5, which by the definition of absolute value means x is 5 or it's negative 5. So what are my x-intercepts? We have 2 of them, and they're the points 5, 0 and negative 5, 0. Those are my x-intercepts. All right, so we don't have much left to talk about in this particular video. All we have left is finding domain and range of functions rather than just relations. So earlier in this video, we defined the domain and the range. We said the domain is the set of all the x values of our relation, and the range is the set of all the y values of the relation. Remember that functions are relations. They're just very special relations. So our domain is still going to be the set of all the x values, and the range is going to be the set of all the y values. So first we're going to find domain and range from a graph. So here's our first one. We have a graph, And we have a few points on our graph. Well, it would help if I could graph straight. There we go. All right. So remember, the domain is your x values and the range is the y values. So looking at this graph, I only have 4 points on this function. For my domain, let's just list all the x values of the points. This point has an x value of -2. This one has an x value of -1. This one's an x value of 1. And my last one's an x value of 2. So my domain is -2, -1, 1, and 2. Now for my range, we need y values. Y value of this first point is +4. My second point has y value -1. This one has a y value of 1 and a y value of 2. So my range is 4, -1, 1, and 2. That one's not too bad. But again, we don't always have functions that are just individual points. So sometimes when we're writing the domain and range, we can't just write a list of values. For part B, we're going to have another graph, but we're not going to be able to list out every single value in the domain and range like we just did. So for this graph, let's see here, I have points here, down here, and right about here. So here is my function, and it has an arrow on the end, so it's going on forever in that direction. Let's find our domain and range of this particular function. Remember, your domain is all of the x values. So to figure out the domain, we need to figure out the smallest x value possible and the largest x value possible. To find the smallest x value possible, see how far the graph goes in the left direction. Well, I have this arrow here, so this graph is going on up forever and also to the left forever. So do I actually have a smallest x value? No. So we're just going to call it -infinity. We go all the way down as far as we can. But for the largest x value, my graph stops right here, where x is equal to 1, 2, 3, 4. So I have -infinity to 4. And now I just have to figure out how to write this in what's called interval notation. I've already started it here. You list the smallest value and the largest value, and then we just have to use parentheses or brackets. Parentheses are used whenever that value is not actually included, and brackets are used when the value is included. So you would use a parenthesis anytime you have an open circle on your graph. If you have a closed circle like we have on 4, you use a bracket. Now, for these infinities, you're also going to need parentheses, because when we're working in the real number system, you can't actually touch infinity or -infinity, so they're not actually included in the domain. Now let's look at the range. My range is all the y values. Try to find the smallest y value first. That would be how far down does the graph go. And the lowest point on the graph is right here, where my y is -4. And what's the largest y value? Well, my graph goes up forever, so we go all the way up to infinity. Now we just have to figure out our brackets and parentheses. Again, closed circles are included, so I have a bracket on that -4. Infinity is not actually included, so we have a parenthesis. So the way I wrote my answers here is called interval notation. There are other ways to write your domain and your range, but this seems to be the most popular way among most mathematicians. So I would use interval notation unless I'm told to use something different. Now, that's how we find domain and range looking at a graph. But what if you're given an equation for your function? Can you find the domain and range from the equation without actually graphing the whole thing? The answer to that is, of course, yes. When you're trying to find the domain and range when you're given an equation, the easiest way to do it is to look at what is not allowed. Think about our real numbers. What are things we're not allowed to do? We're not allowed to divide by 0, and we're also not allowed to have square roots of negative numbers, or fourth roots of negative numbers, or any even root of negative numbers. So when you're trying to find the domain of a function, you need to make sure you're not dividing by 0, and you're not taking even roots of negatives. As long as you take care of those things, everything else is fair game. So let's do some examples of this. Find the domain. My first function is f of x is equal to x minus 2 over 3x plus 1. So we have to figure out, does anything cause problems on this function? Do I need to worry about taking even roots of negative numbers? No. I don't have any roots at all, let alone even roots in this particular function, so that's not a concern. However, I do have a denominator, so there is potential to divide by 0. To figure out if we end up dividing by 0 anywhere, you take your denominator and you set it equal to 0 and try to solve that equation. So I'm going to move the 1 to the other side to get 3x equals negative 1 and divide by 3. Now, the only thing that's kind of tricky about using this technique is when you solve that equation, the answer you get to that equation is a value that is not in the domain. Your domain is actually every single other number except for negative 1/3. So if I'm going to write that in interval notation, we're going to start all the way down as far as we can. So negative infinity until we reach negative 1/3. But I'm not going to include negative 1/3, so I'm going to use a parenthesis. And then I'm going to start again, still at negative 1/3 with a parenthesis, going all the way to infinity. And in between these two intervals, I write what looks like a capital U. That stands for union. So I'm saying my domain is both of these pieces. And this is just a fancy way of saying every single number that is a real number and not negative 1/3. All right, let's do 2 more of these. What if I have g of x equals x squared over 5? Do I have any roots to worry about? Any even roots of negatives? No, I don't have any roots in this function at all, so I don't have to worry about that. Do I have to worry about dividing by 0? I do have a denominator in this function, but my denominator is 5. 5 is never going to be equal to 0. So my domain is everything. It's all of my real numbers, negative infinity to positive infinity, parentheses on both sides. Last example, finding the domain from an equation. Let's have the function k of x equals the square root of x plus 3. Now, this time we have to be concerned about taking a root of a negative number. This is a square root problem. We cannot take a square root of a negative when we're working with real numbers. So I'm going to need to make sure that this x plus 3 is not negative. Do I have to worry about dividing by 0 in this problem? No, I don't have any division at all, so that's not a concern. So to find my domain, I know that I want all of that stuff under my square root to not be negative. So I want x plus 3 to be greater than or equal to 0. when I solve this inequality, I get x is greater than or equal to -3. This tells me that all of these values are in the domain. Those are the values that give me something underneath my square root that I can actually evaluate. So x is greater than or equal to -3. That means the smallest value for x is -3, and it's all of the numbers bigger than that, so all the way up to infinity. That is my domain. All right, we have one last example to finish up this video. We're going to look at a graph of a function and answer a lot of questions about it. Let me draw my graph real quick. I am a terrible grapher, so you guys might have to use your imagination a little bit while you're watching this video, but I'll do the best I can to make it as accurate as possible. All right, there's the graph of my function. This is f of x. And we're going to answer a lot of things about this function. First, let's find f of -2. So f of -2, that is asking us what is the y value when my x value is -2. Remember, your x was what was inside of the parentheses in our notations. That's how I know they're asking me for a y value. F of -2, we go to where x is -2 on the graph and find the y value of that point. And I get my y value is equal to 1. So I get 1 for f of -2. What about f of 4? So remember, this is asking us, what is the y value when my x value is 4? Well, my x value is 4. 1, 2, 3, 4. Right there. And I don't actually have a point on my graph there. I have a hole. So does f of 4 even exist? No. This is undefined because I have a hole there and not a point. Part C, we're going to find all x values for which f of x is equal to 3. So they want us to find the x values that give me a y value of 3. So let's look at our graph. Where is y equal to 3? This point right here is where y is equal to 3, and that is the x value, -4. Part D is similar. Let's find all x for which f of x equals 1. So that again, find where the y is 1, that's right here. And it's going to be a lot of x values. It's everything on this part of my graph. That is, x is starting at -3 and going to -1, and it includes all of the values there. Don't just list -3, -2, and -1 because we have all the little fractions in there as well. So we have to write this as an interval. All of the x between -3 and -1 with brackets because they actually equal 1 at those points too. All right, I have to erase our work over there because we still need to find the x-intercepts, the y-intercept, domain, and range. I'll leave that last one up there if you still need to write that down. So let's find our x-intercepts, if there are any. Remember, that is where we touch the x-axis, my horizontal axis. Where does my graph touch the horizontal axis? Only at this point here, the point 0, 0. What about y-intercept? That's where we touch the y-axis. And that only happens, again, at that exact same point, 0, 0. It's okay that our x-intercept and our y-intercept are the same point. It actually happens a lot more than you might think. It doesn't always happen, though, so don't assume that that's always going to happen. And then let's find our domain, and then last will be our range. Finding the domain, remember, domain is your x values. Start going to the left of the graph. How far to the left do we go? Infinitely far. We're going to the left forever. So my domain starts with negative infinity. And what's the largest x value? 4, except it's not included. I have an open circle there. So I get a 4 with a parenthesis and not a bracket. For the range, we do something similar. Find the smallest y value, which is from this hole again. What is the y value there? Negative 4, but it's going to have a parenthesis because it has that open circle and not a closed circle. What is the largest y value? Well, my graph is going up forever because I have that arrow on the end. So it's going up to positive infinity. Parenthesis on that because, again, when we're working with real numbers, you can't actually touch infinity. It's not really a number, it's more of a concept. So that's all I have for you today on this first video on functions and relations. If you're a current student of mine, feel free to ask questions through email or office hours, or you can drop a comment down below. And that goes for anybody watching this, not just my current students. You can drop questions down below, and I'll try my best to answer them. And I will see you next time.